And so today, we want to consider heat energy 1. What is heat energy? Well, heat energy is a form of energy also known as thermal energy. It is that energy that flows from a hot object to a cold object due to temperature difference. It's important to note that heat is a scalar quantity, or heat energy is a scalar quantity, and it is measured in joules because it's a form of energy. Then another concept connected to heat is temperature. What then is temperature? Temperature, in a layman term, can be defined as the degree of hotness or coldness of an object. But from the kinetic or the molecular point of view, we can say that heat is the measure of the average kinetic energy of the molecules of a body. Temperature is measured with the aid of a thermometer. It's also a scalar quantity, and its SI unit is Kelvin. So now we want to look at next the effect of heat. Effect of heat. You see, heat can cause any of the following. 1, change in temperature. When an object is heated, the temperature rises except during change of state, because during change of state, the temperature of an object remains constant. Next is change of state of a body. When a solid is heated to a sufficient high temperature, which is up to the melting point, the solid melts and it melts into liquid. And when a liquid is heated also sufficiently to its boiling point, it vaporizes or evaporates to gas. And that's change of state from solid to liquid and liquid to gas. Again, is the expansion of a body. Generally, when objects are heated, be it a liquid, be it a solid, and be it gases, they tend to expand. And that is basically what we actually want to consider under this study. Again, is change in physical properties. You see, the magnetic property of a substance, its resistance, density, elasticity, conductivity, etc., can change as a result of the object being heated. Again, another effect of heat is thermionic emission. You see, when metals are heated to a sufficient high temperature, they tend to emit electrons, and that process is known as thermionic emission. Again, it's change in chemical properties. The chemical constituent of an object can change when the object is being heated, or you can say that's an example of chemical change. And lastly is change in pressure. Another effect of heat is change in pressure, that when an object is heated, most especially fluid, their pressure tends to increase. Now, let's consider expansion of solids. Expansion of solids. You see, when solids are heated, it's already an established fact that they tend to expand. Sometimes these expansions are not noticeable with the eyes because they are just so small that the eyes may not dictate it. But there are experiments that prove that solid expand when heated. And two of those experiments, or few of those experiments, are the ball and ring experiment and the bar and gauge experiment. You see, for the ball and ring experiment, without being heated, this ball goes into this ring easily. But taking this ball and hitting the ball and try to fix it into this ring, it no longer enters again. That shows that the ball itself had expanded because it was heated. The same goes for the bar and gauge experiment. You see, without being heated, this bar fits into this gauge. This is the gauge. But the moment the bar is being heated, and then one try to fit it into this gauge, it no longer enters, meaning that the bar has expanded. So this clearly proves that solids expand when heated, even when it cannot be dictated with the eyes. So let's consider the various ways in which expansion of solids can be measured. So measurement of expansion in solids. You see, there are various ways in which the expansion in solids can be measured. And they are: 1, linear expansivity. This measures how the length of a solid expands. And we have area expansivity, which is also known as superficial expansivity. This talks about how the area of a solid expands. And then we have the volume expansivity, and this measures how the volume of a solid equally expands. So let's look at the very first one, linear expansivity, represented with the Greek letter alpha. You see, linear expansivity is the increase in length per unit length per degree rise in temperature. So linear expansivity is the increase in length. That is change in length. That's what increase in length means. Per unit length per degree rise in temperature. So this is it. Where L2 here is the new length at the new temperature. L1 is the initial length at the initial temperature. Then theta 2 is the new or the new temperature, yeah, and theta 1 is the initial temperature. But you see, theta 2 minus theta 1 can be represented by change in temperature. So this is simply change in temperature. So substituting this for change in temperature, we have this as our formula for linear expansivity. Again, from this formula, which I can call equation 1, we can as well say that upon cross multiplying, if we cross multiply this, we have that alpha over 1, let's show that, is equal to L2 minus L1 over L1 change in temperature. If we cross multiply this times this will give us L2 minus L1, which is equal to alpha L1 change in temperature. But we all know that L2 minus L1 can also be written as change in length. So we can say change in length is equal to alpha L1 change in temperature. So this is another formula which we can use, because sometimes the question can say calculate the change in length. Change in length is simply linear expansivity times the initial length times change in temperature. Again, you see, I can call this equation 3 and call this equation 2. You see, from equation 2, we can calculate get the formula or equation for the new length. Meaning that from equation 2, we have that L2 minus L1 is equal to alpha L1 change in temperature. If we bring this to this side, we get that L2 is equal to L1 plus alpha L1 change in temperature. If you look at this carefully, what is common here is L1. So L1 factorized out to give me L1 in L1 will give me 1 plus L1 divided by what is we have on this side, we have alpha and change in temperature left. So this is the formula for the new length, which I call equation 4. So sometimes the question is asking you to calculate the new length, which is L2. Sometimes it's asking you to calculate change in length, and that's the formula we are going to use. Sometimes it's asking you to calculate alpha, which is linear expansivity. In some cases, you are asked to calculate L1. So whatever you have to calculate, it's not a problem actually, but we have these formulas written down so that it makes our calculation easy. So let's take some examples on linear expansivity now. Example 1. A metal of length 15.01 centimeter is heated until its temperature rises by 60 degrees C. If its new length is 15.05 centimeter, calculate its linear expansivity. Let's write out what we are given here now. We are given the initial length, 15.01 centimeter. Somebody said, let's convert this to meter. Well, you don't need to do that. If you convert to meter or you don't convert to meter, you still get the same answer for linear expansivity. That's number 1. And even when we are asked to calculate not only linear expansivity, even new length, if you are given centimeter, just use it like that and leave your final answer in centimeter. So take note of that. So you don't need to convert. So this is our L1, 15 centimeter. Then it's heated until temperature rises by. Whenever you hear temperature rises by, temperature increases by, the word by shows the increase in temperature. And so take note that our change in temperature rises by is 60 degrees C. Another thing you need to note here that you need to convert your temperature to Kelvin. And I will explain that as we proceed. You see, now if its new length is, we are given the L2 to be equal to 15.05 centimeter. Calculate its linear expansivity. We know that linear expansivity is given as L2 minus L1 over L1 change in temperature. So our L2 is given as 15.05 minus L1 is given as 15.01 over 15.01 times temperature change, which is 60. So let's quickly do that now. This will give us 4.44 times 10 raised to power minus 5 per degree C or per Kelvin. Whichever one you want to use, that's correct. So that's that for this example 1. So let's take example 2. A copper rod whose length at 30 degrees C is 10.0 centimeter is heated to 50 degrees C. Find its new length. Take alpha, that is linear expansivity of copper, as 0.000017 per Kelvin. Now, we can see that the formula for new length, or let's write out what we are given first. So, our given now, we have our L1 to be 10 centimeter. We're also given our initial temperature, θ1, to be 30 degrees C. And then we are given our θ2 to be 50 degrees C. We are given our alpha to be given as 0.000017 per Kelvin. Okay? And so our change in temperature here will simply be 50 minus 30, and that's 20 degrees C, because θ2 minus θ1. Now, very important now, even if someone say, why don't we convert to Kelvin? I want to convert to Kelvin. There's actually no need, because if you do convert to Kelvin, you see have the answer as 20, meaning that if you convert this to Kelvin, you see, that's plus 273. You have 323 Kelvin. And you convert it to Kelvin, you have 303 Kelvin. And by the time you subtract 323 from 303, you still get 20 as a difference. So that's my point, that any formula or any equation in physics that involves change in temperature, there's no need to convert from degree C to Kelvin or Kelvin to anyone. Use it as you are given. You get the same answer. So take note of that. That's cut across things like specific heat capacity, where heat is given as MC change in temperature. You don't need to convert the temperature given here, either it's in Kelvin or is in degrees Celsius. But if we are working with things like the gas laws, where we have, for example, now we have the Charles law, V1 over T1 is equal to V2 over T2. Yes, right here, you need to convert, because this is not change in temperature. These are temperatures, single temperatures, or absolute temperatures. So you must convert to Kelvin if you are given in degrees C, but not for things that have change in temperature. So that's about that. Let's continue with our question now. So we need to calculate the new length. We have it, we've derived that formula for new length is given as L2 is equal to L1 into bracket 1 plus alpha change in temperature. And so our L1 is given as 10 into bracket, or 10.0, which is still 10, into bracket 1 plus our alpha is given as 0.000017 times change in temperature is given as 20. So at the end of the day, if you evaluate this completely, you have 10.0034 centimeter. So that's that about that. Like I said, you don't need to bother yourself about converting from Celsius for centimeter to meter and the rest of it. Like, just leave your final answer in centimeter as well, because the initial length was in centimeter. So let's take example 3. Example 3, a wire of length 100 meter at 30 degrees C has a linear expansivity of 2 times 10 raised to the minus 5 per Kelvin. Calculate the length of the wire at a temperature of minus 10 degrees C. And so here, we have it that we are given the first of all, the initial temperature as 30 degrees C. And then we are given our linear expansivity alpha as 2 times 10 raised to the minus 5 per Kelvin. We're also given our final temperature as minus 10 degrees C. And now we have to get, we are given the initial length as 100 meters. And we have to get now the new length. Okay, again, we know that our new length is given as L1 into bracket 1 plus alpha change in temperature. Already, our change in temperature is theta 2 minus theta 1, and that will give us minus 10 minus 30, which is minus 40. But mind you, when solving, we are using the absolute value, which is just 40, ignoring the negative value. And so right here now we can say L2 becomes L1, which is 100, into bracket 1 plus the alpha is given as 2 times 10 raised to the power minus 5, then times change temperature is given as 40. So eventually we have 0.08 meters. That's the final answer. So that's that about that.